Hello, hiers, welcome to lesson 4. So it's going to be ionisation, energy and electronegativity we're going to go into today. Now, got a wee starter here, so I'll go through the questions and then we can pause it after. So question 1, the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state is known as what? Okay. Question 2, I want you to write the second ionisation energy equation for boron. And I want you to include the delta H value for that. So you're writing the second. Okay, so the first one's been done. I want you to write the second. Question 3. Why is there no value for the second ionisation energy of hydrogen? Question 4. We've got Mg positive G going to Mg3 plus G plus 2 electrons. What would the delta H value for that be? You will need your data book, obviously, for all this. And question 5, explain why argon has a higher first ionisation energy than sodium. So pause the video, do the questions. I'm just about to go over the answers. Right, so question 1, what is the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state? It is the first ionisation energy. So well done if you got that. Question 2, write the second ionisation energy equation for boron. So the first one's already happened. So B in the gaseous state going to B plus in the gaseous state. That's already happened. So we're starting with B plus. Yeah, we start with B plus and then that loses another electron to give us B2 plus. Now the important thing is well, you obviously get the charges right, but you remember the state symbols, okay? And also, we've lost an electron, okay? So you have to have that exactly as I've written it. Question 3, why is there no value for the second ionisation energy for hydrogen? Quite simple. Hydrogen only has, B plus going to B2 plus, that value was plus 2427 kilojoules per mole. Okay. Why does hydrogen, hydrogen only has 1 electron, so once you've removed that electron, you can't remove a second one. Okay, now if you can't remove a second one, let me just move this over, then it won't have a second ionisation energy value. Question 4, I'm going to come back to because we're going to do it together. Question 5, however, explain why argon has a higher first ionisation energy than sodium. So, if we look at our periodic table, we'll try and focus this a wee bit. Sodium, you'll notice, is over here, and then argon is over there. So it's in the same period. Okay, so why is argon got a higher ionisation energy? Well, as we go along the period from sodium to argon, yeah, a proton is added each time. Okay, so argon has more protons. Let me just move this over. Argon has more protons than sodium. Okay, what does that mean? It means it's created a stronger positive nuclear charge. Okay, now what does that nuclear charge do? It pulls the outer electrons closer to the nucleus, and because the electrons are closer to the nucleus, it's harder to remove the electron. Okay, and if it's harder to remove the electron, of course the ionisation energy has to be higher in argon. Okay, so make sure you've got that. Right, question 4, Mg plus to Mg3 plus. Now if we look at our data book here, we look at Mg. Now the first ionisation energy is 738, however, it's already been done. Okay, we've already went from Mg to Mg plus, we're starting with Mg plus, so we don't need to include the first one. Okay, so because it's going through 2 ionisation energies, it's going to Mg2 plus and then Mg3 plus, we need to add the second and third, so that is 1451 add 7733. So that's 1051 add 7733. I don't actually have I could do it in my head, but let's just use a calculator. 7733. So we have 9184. Okay, so it's plus. Why is it plus? It's endothermic. That's what that plus sign means. Okay, that plus means it's endothermic. So it's plus 9184. And don't forget your units, kilojoules per mole. Okay, so well done if you got that. Right, last lesson I did say I was going to go back to the start, but I never did because I completely forgot. So I'm just going to do that now. That's the equation for sodium. So sodium in the gaseous state going to sodium ion in the gaseous state plus an electron, and that's the value plus 496. And that's the same for oxygen. Okay, so just check that your answers match up with mine. Now what I do want to point out, and it's very important actually, note we do not write the diatomic symbols. Okay, so for chlorine we don't write Cl2, for oxygen we're not writing O2. And why is that? It's because our our definition is that from 1 mole of atoms. If we have Cl2, that's no longer an atom, that's a molecule. So remember, when you're writing, don't get confused. We don't write the diatomic ones. Okay. Right. Let's get started. The last video went on for about 40 minutes, so I never wanted to carry that on any further. So we're just going to, there's one last wee bit to do with ionisation energy, then we can go straight into electronegativity, and that's probably the easiest one to do. So ionisation energy, usually you would get a question like this. Okay, so we'll do our 2 questions first. Why is the second ionisation energy far greater than the first in, let's go for sodium. Okay, and then the second question, same idea, in, let's go for magnesium. Okay, so in magnesium, why is the third ionisation energy far greater than the first and second? And what I mean by that, okay, if we look at our data book here, what was it? It was sodium, wasn't it? Yeah. So sodium, you'll see the first one is 496, and then the second one jumps up to 4562. Mental. Okay, so why is there such a big jump between the first and the second, but you don't really get that same jump between the second and third? Okay, if we look at magnesium, okay, the first one's 738, and then the second one is 1451, and then the third one, look at that, 7733. It's massive. Yeah, that's like over 6,000 of a jump, but then you don't get that same jump going from third to fourth. So why in sodium is there a big jump between the first and the second, and then in magnesium between the second and third? And even aluminium, there's a big jump. You've got 578, 1817, 2745, but then the fourth one goes up to 11,577. So why is there this big massive jump? Okay, and to explain that, we need to write the electron arrangements out. So we're going to start with sodium. Okay, so if we just go for sodium, normal sodium, a sodium atom, if we look at our data book, the sodium electron arrangement is 281. Okay, so we'll write that there, 281. So if we go through the first ionization energy, that goes to sodium plus, and then because we've lost an electron, that has an electron arrangement of 28. Okay, now the question is, why is the second ionization energy far greater than the first? Now, if we go through the second ionization energy, you might already be able to work it out. We're going from 28 to 27. Okay, now what we've done in the first ionization energy, we've achieved a stable electron arrangement. Okay, now that's what atoms want, that's what ions want. They have that stable electron arrangement. Now if we try and take away an electron from a stable electron arrangement, we're going to have to put in a lot of energy, because believe me, the ion doesn't want that to happen. Once it's achieved its stable arrangement, it's happy. Okay, if we try and remove another electron, we're going to have to put in a lot of energy. Okay, so there's two reasons for this. Okay, so the first one, during the second ionization energy, okay, the electron is removed from a stable electron arrangement. Okay, now you would get 1 mark for that. Usually these questions would be 2 marks. Okay, now you get 1 mark for that. However, with R and higher, we do need to expand our answers a wee bit. Now, the second point you would need to make is the electron is closer to the nucleus. Now, if I just get my wee markers, if we go from this electron here that we're removing, it's from it's from the third shell, so it's furthest away. Okay, so it's the furthest away from the nucleus. Now, if we want to take an electron here, we're taking it from the second shell. So as you can see, the second shell is a lot closer to the nucleus than the third shell. Okay, and that's why there's such a big, massive jump. It's because that electron is closer to the nucleus. Okay, however, again, it is higher. That isn't enough. Okay, so the electron is closer to the nucleus. You need to expand that, where it is pulled more strongly by the nucleus. Okay, and you have to say that. So the important thing there is getting removed from a stable electron arrangement. Okay, it's closer to the nucleus and it's pulled more strongly. Okay, and you need to say both of those points to get the 2 marks. The majority of people, from my experience, they say this one all the time, they get 1 mark. If you really are pushing for that A being higher, you need to be getting the 2nd mark as well. Okay, so the electron is closer to the nucleus, where it is pulled more strongly by the nucleus. Okay, so again, it's harder to remove. That's why that energy is far greater. Now, if we go for the second one, magnesium. So magnesium is 282. Okay, if we go through the first ionization energy, that goes to Mg plus, which is 2, 8, 1. If we go through the second ionisation energy, that goes to Mg2 plus, which is 2, 8. So we're stable. Okay. The question is asking, why is the third ionisation energy far greater than the first and second? Okay, so if we do a third, we're going from 2, 8. So that goes to Mg3 plus. We're going from 2, 8 to 2, 7. So again, the key thing here is we're going from a stable electron arrangement to an unstable electron arrangement. So it's the same idea. Okay, so in it's pretty much the same answer. This time, instead of during the second, you would say during the third. Okay, so during the third ionisation energy, the electron is removed from a stable electron arrangement. Okay, 1 mark. What else do we need to say? Well, it just went from 281, that's in the third, but that's now in the second shell. Okay, so the electron is also closer to the nucleus, where it is pulled more strongly by the nucleus. Sorry, that's my dog barking. Murray. Right, so again, the key word is that electrons getting moved from a stable electron arrangement. Right, sorry, I'll be back now. Just getting my dog. Right, sorry. Where were we? So the electron is it's closer to the nucleus, and it's getting pulled more strongly by the nucleus. And you have to say that. You have to say it's closer to the nucleus, and it's getting pulled more strongly. Okay. Right. So that's ionisation energy done, dusted. Next one. Or should be a subheading. Electronegativity. Okay. Right, so first things first, I'm going to give you the definition of that. Okay, so electronegativity, it is a measure of the attraction an atom has for bonded electrons. Okay, and again, such an important word, such an important term. You have to say bonded electrons. Okay, so it is a measure an atom has for bonded electrons. Now, this question comes up very often. I think, don't quote me, in the last 5 years, this question's came up 3 times. What do we call the measure of attraction an atom has for bonded electrons? The answer, electronegativity. What is the definition of electronegativity? You say that. You have to memorise it. Very much, I know I keep saying it, but in National 5, when you had to memorise homologous series, isotopes, isomers, blah, 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 you need to know electronegativity. okay, word for word. Now, what we mean by that, okay, if we, that way there, so the higher the electronegativity, the closer the bonded electrons are to the atom. Now, what we mean by that, okay, if we just go for H and H, maybe make a wee note here actually. Values found on page 11 of the data book. Okay, so the values are found on page 11 of the data book. Now, if here it is, here's page 11 here. The electronegativity values are down the side, so it's on the same page as the ionisation energies. You've got the wee electronegativity scale here. So it ranges, it can range from, well, we've got 2.2, we've got 1, 0.8. The highest value we've got 4 is fluorine, so it ranges from, what, 0.8, I think is the lowest, all the way up to 4.0. Okay, so the higher the electronegativity value, the closer, the greater that attraction, the greater that atom, the greater attraction that atom has on bonded electrons. So what we mean by that, H and H has an electronegativity value of 2.2. Okay, now H is 2.2, H is 2.2. So because that's equal, what happens, try and make this a bit more clearer, is that electrons lie bang in the middle. Yeah, because they've got equal attraction, so the electrons right in the middle. Yeah, however, if we go for H and F, H is 2.2, F is 4. Okay, so because F has a higher electronegativity, what that means is that the electrons will sit closer to the fluorine. Yeah, that's all that means. Now, when we do the bonding structure unit, we go into a lot more detail about electronegativity. Electronegativity is massive in bonding structure. However, for the purposes of trending, that's all you need to know. Okay, so what we need to look at now are the trends. So, going across a period, electronegativity, well, you tell me, what does it do? As we go across the period from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, what's happening? It's going up. Okay, so going across the period, electronegativity increases. Now, going down a group, what happens to the electronegativity? Let's have a look. So as we go from what, lithium, sodium to potassium, so lithium, sodium, potassium, rubidium, what's happening? It's going from 1 to 0.9 to 0.8 to 0.8, so it's decreasing. Okay, so going down a group, electronegativity decreases. So obviously we can see from the data book that's exactly what's happening. However, we need to explain it. Okay, so let's go for our explanations. Now, we've already done this, yeah? To be honest, you could probably already give me an answer already. So the very first one, as we go along the period, okay? As we go along the period, what do we add? Well, hopefully, you should know, is that we add a proton, okay? So a proton is added. Now, if we add a proton, what does that mean? That proton creates a stronger positive nuclear charge. Okay? And what does that stronger positive nuclear charge do? It pulls the outer electrons closer to the nucleus. Okay? Now, if those electrons are getting pulled closer to the nucleus, that must mean that atom has a greater attraction for the bonded electrons. Okay, so if it's pulling the outer electrons closer to the nucleus, instantly that tells us electronegativity increases. Okay, so that's all you have to write. All you have to write is a three sort of main points, and then electronegativity increases. It's not like ionization energy where you have to say it's harder to remove the electron or it's easier to remove the electron. All you have to write is electronegativity increases. So we're writing the same answer as we did for atomic size, but instead of saying atomic size decreases, we're saying electronegativity increases, and that's it. Yeah, that honestly, it's no, that's as hard as it gets. Now, as we go down a group, what happens? What do we add as we go down a group? An extra energy level is added. Now remember, if you're getting asked this in an exam, you have to be specific. Okay, so if it's talking between, I don't know if you can see that, if it's talking between nitrogen and arsenic, you need to say that 2 energy levels have been added. Okay, so be specific. So as we go down a group, an extra energy level is added. What does that extra energy level do? Well, the extra inner energy level provides a stronger shielding effect. And what does that shielding effect do? It weakens the force of attraction between what? Between the outer electrons and nucleus. Okay, so if you've got a weaker attraction between the nucleus and the outer electron, yeah, the electronegativity decreases. Okay, so electronegativity decreases, and that's all you have to say. Okay, you don't have to go into detail about what electronegativity means, because if you do that, chances are you're going to contradict yourself. Okay, so just write your points. So if it's along the period, again, I'll highlight it. It's the proton getting added, it's the stronger positive nuclear charge, and it's the pull off the outer electrons that brings it closer to the nucleus. Okay, as we go down a group, an extra energy level is added. Okay, where's that pen? The inner energy level, that provides a stronger shielding effect. Okay, what does that shielding effect do? It weakens the force of attraction between outer electrons and nucleus. Okay, and again, to be honest, I've not actually, this wee bit here, I've not actually taught anything new. Yeah, it's the same thing over and over again. We should be experts at this. Yeah, we should be. So, that's it. That's trends done and dusted. I'm going to put some questions on though, as I always do. So, questions to try. So let's go for the first one. Right. Why is the fourth ionization energy much greater than the third? Okay, so first, second, third ionization energy, wee bit of energy, but then the fourth one, boom, it shoots all the way up. Why is that? Okay. Question 2. Explain the trend in electronegativity so explain the trend in electronegativity as we go from lithium to go for fluorine. And question 3, explain why calcium has a lower electronegativity than magnesium. Okay, so why does calcium have a lower electronegativity than magnesium? Fourth one, just because it popped into my head. What is meant by electronegativity? Okay, try and do this from memory. I know we've just done it and you could literally just look over the next page, the previous page, but try and do it from your memory. Okay, so what is meant by electronegativity? Right, that's us. Thank you.